can I just remind you of what happened in the previous lesson? So in the previous lesson, we introduced simple harmonic motion, SHM. Simple harmonic motion occurs when you have an object which is moving in such a way that there is a force acting on it which is directed towards the origin, its equilibrium position, O, and is proportional to its displacement from that position. SHM will always lead to a differential equation of the form, let me just get this correct, this form here. d2x by dt squared is equal to a negative constant times x. We can call the negative constant minus omega squared. X is the displacement, t is time. And this can be solved using further maths methods to give a solution of the form x is a cos omega t plus b sine omega t. So what that means is the particle oscillates about its equilibrium position. Its motion alternates between being a positive and a negative displacement. There are other certain values that we can write down. If we know what the other initial conditions are, we can work out A and B and so on and so forth. Now, what we're going to do today is what is more likely to turn up in an exam, which are two refinements to the simple harmonic motion model. The first refinement is to introduce a damping force, which means a resistance to motion. Okay, so that might be air resistance, for example, could be a damping force, or friction could be a damping force. Now I'm going to set up a differential equation of this type in a minute, but you just have to trust me, this will lead to a differential equation of this form. d2x by dt squared plus k dx by dt plus omega squared by x. The d2x by dt squared is the acceleration. The k dx by dt term comes from the damping force. We're going to assume it's proportional to and opposing the velocity, which is dx by dt. This term here comes from the force which produces simple harmonic motion. Now, these differential equations can be solved using further maths methods. That's what we're going to do. And interestingly, they will give different forms of solutions, so different types of motion, depending upon the values of k and omega. So I'm going to just go through solving some of these, and then we'll do perhaps a more realistic exam question after that. So I want to find the general solutions of these differential equations for damped simple harmonic motion. In each case, I want to sketch the graph of x against t, or a possible graph of that form. So the first differential equation I'm looking to solve is d2x by dt squared plus 4dx by dt plus 3x is equal to 0. Now, differential equations of this form are solved by writing down the auxiliary equation, which in this case will be m squared plus 4m plus 3 is equal to 0. And then solving that to find values of m. And in this case, that gives me m is equal to -1 and -3. The general solution, the complementary function, is therefore going to be, it's x instead of y, is a e to the minus t plus b e to the minus 3t. And there's no need for a particular integral because there's 0 on the other side. So what does this mean happens in this type of situation? Well, these two terms are both negative, both exponential decaying terms. So all this means really is the displacement decays exponentially with time. So the object is going to move. It's not going to oscillate at all. It's just going to get closer and closer and closer to its equilibrium position. Now, this is called heavy damping, and this comes into play when the damping force is very, very large. If you had an object on a spring and it was in, say, treacle or golden syrup or something, it wouldn't actually oscillate. It would just move towards its equilibrium position. So this situation is known as heavy damping. There is a second case which is known as critical damping. So again, here is my differential equation. It's almost the same as before, just one number difference. Let's see what happens if we solve this. So this is going to have an auxiliary equation of m squared plus 4m plus 4 is 0. And this has repeated roots. So m is minus 2. It has repeated roots. The general solution of this is therefore x is e to the minus 2t into a linear function, which is at plus b. That's what that's going to give you, ladies and gentlemen. And let's see what that leads to then. So what's a graph of that going to look like? Well, it's a product of an exponential decay term and a linear term. So what this means can happen is the following. If t is small, the function can increase linearly, approximately. But then as t gets large, the exponential decay term takes over and it decays exponentially. Now, this is kind of the cutoff between two different types of behavior, heavy damping and light damping, which we'll come into in a second, and this is known as critical damping. Light damping occurs in the following sort of situation. So again, same differential equation, solve it the same way, but we'll see something quite different happens. So this gives an auxiliary equation of m squared plus 4m plus 5 is 0. And this one, solve it on your calculator, turns out to have complex roots of the form m is minus 2 plus or minus I. So consequently, the general solution corresponding to this type of motion is going to be x is e to the minus 2t brackets a cos t plus b sine t. So this is the product of an exponential decay function and a trig function. So this is what this is going to do. The trig function is going to make the object oscillate. However, the exponential decay term will reduce the magnitude of the oscillations as time goes on. So this will give a graph of x against t, which is going to look something like this. So it is oscillating, but the magnitude of the oscillations is going to decay as time goes on. Now, in general, if you are solving a differential equation of this type, one of these three kinds of situations will occur. And it depends upon whether the quadratic has real or complex roots, which depends upon its discriminant. And the discriminant, b squared minus 4ac, is just k squared minus 4 omega squared. So one of three things can happen. If the discriminant is positive, you will have real distinct roots, which actually will both turn out to be negative always. You'll get a general solution of the form x is a e to the minus alpha t plus b e to the minus beta t. This is known as heavy damping. If the discriminant is 0, you'll get repeated roots and you'll get a general solution of the form e to the minus alpha t times at plus b, an exponential decay term times a linear term. This is critical damping. If the discriminant is negative, you will get x is e to the minus alpha t times a cos beta t plus b sine beta t. That's because the roots will have the form alpha plus or minus beta I, and this is known as light damping. So there will still be some oscillation, but the magnitude will decay. That's because the damping is making it slow down. Okay, folks, so that was just to introduce you what's going to happen. Can I now have a go at an exam type question on this topic? So this is example 1 on page 10. So students, we're given the following situation, a particle of mass 0.5. Anyway, there's quite a lot going on here. Can I just say, I think one thing I'm going to do before I do this is I am going to draw a line down the middle of the page because I know I've got a lot of work to do on this one. Whoops, I didn't want that to happen. Didn't want that to happen at all. Let's just extend the line of the page all the way down the page. And then I'm going to go down the left-hand side and down the right-hand side afterwards. So here we are told a particle of mass 0.5 kilograms moves on a horizontal line. After t seconds, the displacement is x meters and the velocity is v meters. So this just means m is 0.5. A force of magnitude 8x newtons acts on the particle directed towards the fixed point. So that's the kind of force that would produce simple harmonic motion. The particle is also subject to a resistance, i.e. a damping force of magnitude kV. So we're going to assume that the resistance is proportional to the velocity. But given the initial values of x and v, I've got to prove this differential equation. So can I draw a picture to illustrate what's going on here? So you've got some point O, and then we have our particle. The forces that we are interested on it are, it's got a force of magnitude 8x directing you back towards the origin, and also it's got a force of kV directing to the origin. Those are the forces of interest. There will also be vertical forces, which the weight and a reaction, I'm going to ignore those. Okay, so if I use Newton's second law, F equals ma, resolving to the right as positive, the resultant force is minus 8x minus kV. That must equal the mass, which is 0.5 times the acceleration. That's what Newton's second law gives you. That's the equation which connects forces and acceleration. What I'm now going to do is turn this into the differential equation which we see in part A. So what I can do is replace v with dx by dt, and the acceleration, which is dv by dt, which is the second differential of the displacement. So that's d2x by dt squared. So that's going to give me minus 8x minus k times dx by dt equals 0.5 times d2x by dt squared. Now, if you get all of the terms on one side and times through by something to get rid of the 0.5, the differential equation will turn out. So you get every term on the right, you will get 0 is 0.5 d2x by dt squared plus k dx by dt plus 8x. If you times through by 2 or divide by 0.5, you get the differential equation that we wanted. So d2x by dt squared plus 2k dx by dt plus 2 times 8 is 16 times x, as was required. Okay. Now, can I say, for our exam board, actually, they don't often ask you to derive the differential equation from Newton's second law. It's quite likely that in an exam that will just be given to you. If you're asked to do anything with it, I'm sure it would be a show that question, as was. Okay, it then says the following. In the case when k is 4, describe the type of damping and find x when t is 1. Sketch the graph of x against t. So we know that k is 4, so we know that the differential equation we need to solve is d2x by dt squared plus 2 times 4 is 8 dx by dt plus 16x is equal to 0. So to do all of these things, we need to find a formula for x in terms of t, which means I need to solve this differential equation. Then I can work out the type of damping, I can find what x is when t is 1, and I can sketch the graph of the motion. So if you write down the auxiliary equation for this, you'll get m squared plus 8m plus 16 is equal to 0. If you solve that differential equation, you can do it on your, that quadratic equation, you can do that on your calculator. If you wish, ladies and gentlemen, boys and girls, you will get that it has repeated roots, m is equal to minus 4. That's repeated or equal roots. So therefore, the general solution is going to be x is e to the minus 4t into at plus b. This means it has got critical damping. Now, in order to work out what x is when t is 1, I'm going to need to work out the values of a and b. And to do that, I'm going to substitute the initial values of x and v into my differential equation. So I know that when t is 0, x is 1.5. So if you substitute t is 0 and x is 1.5, into the general solution we get on the left-hand side, we get 1.5. And then e to the minus 4t is e to the minus 0, which is 1. A times 0 is 0. So we just get that is equal to b. To use the value for v, I've got to work out a formula for the velocity in terms of time, which means you need to differentiate the general solution. So v is dx by dt. X, remember, is e to the minus 4t times at plus b. If you differentiate that, you're going to need the product rule. So u times dv is going to be a e to the minus 4t plus b plus dv times du by dx is going to give e to the minus 4t. Oops, wait up in there, into at plus b. And that's using the product rule. Can I just make that a bit neater? Minus 40 there. So that's by the product rule. That's what the velocity is. So if you substitute into that when t is 0, v is 4, you will get 4 is the velocity. A e to the minus 4t is just a e to the 0, which is a times 1, which is a. Minus 4 times 1 times b. But that is the same as a take away 6. So if you rearrange that, you will get, whoops, that a is equal to 10. So consequently, the particular solution of this is going to be that the displacement x is e to the power of minus 4t times a, which is 10t plus 1.5. To work out the displacement when t is 1, if you substitute t is 1 into this, you will get that x is e to the minus 4t is just e to the minus 4 into 10 times 1 is 10 plus 1.5, and your calculator will give you a displacement of 0.211 meters. That is correct to 3 significant figures. That's just doing that in your calculator. And this will give you a graph of x against t, which looks like the following. There's t, x. And you can draw the graph on your calculator. It's absolutely fine. You'd have to turn t into x and x into y, but the graph does have this kind of shape. It increases like a linear function, first of all, and we know actually that the initial displacement is 1.5, so that's 1.5 there, and then it decays exponentially. That's the graph of x against t. That's part B done. Now in part C, it says instead, in the case when k is 3, find the general solution of the differential equation and write down the period of the oscillations. So we now know that k is equal to 3. So if k equals 3, the differential equation from part A becomes d2x by dt squared plus 6dx by dt plus 16x is equal to 0. So this will have an auxiliary equation, of the form m squared plus 6m plus 16 is equal to 0. So if you solve that, it will give me m is equal to minus 3 plus or minus root 7i. That's solving that quadratic on your calculator, and it solves to give complex roots. So the general solution, which is what we wanted, is that x is equal to e to the minus 3t brackets a cos root 7t plus b sine root 7t. And this is an example of light damping. Now we can write down the time period of the oscillations straight away. The oscillations are controlled by these two trig functions. cos t and sine t both have a time period of 2 pi. So any combination of those will also have a time period of 2 pi. But the root 7 in front of the t will stretch it by 1 over root 7 in the horizontal direction. So therefore the time period will be 2 pi over root 7. You can do that on your calculator, and that's about 2.37 seconds. Okay, folks, so that's an example of a situation where we had a damping force. The other additional case that we consider is when you have an additional force on the particle which is driving it, which is making it move at some point in some other way, some driving force on the object. This is going to lead to a differential equation in which there is some function of time on the right-hand side. So forced simple harmonic motion will have a differential equation of the form d2x by dt squared plus a constant times x is a function of t. Forced and damped simple harmonic motion will lead to a differential equation of the form d2x by dt squared plus a constant times dx by dt plus a constant times x is a function of t. And these are the style of differential equations that we do know how to solve. You find a complementary function and a particular integral and then add them together. So on page 11, there is an example of this type for us to have a go at, ladies and gentlemen, boys and girls. So we're given the following situation here. Particle of mass 1.5 kilograms moves in a horizontal line. After t seconds, its displacement is x. The particle's velocity is v. A force of magnitude 7.5x acts on the particle directed towards the fixed point. The particle is also subject to a resistance, a damping force of magnitude 6v, and a force of magnitude 12 sine t newtons acting away from the fixed point. So it's 3 forces acting on it. The first one would cause simple harmonic motion. The second one is a damping force. And the third force is a driving force, which makes the particle oscillate. And we're given the initial values of t, of x and v. I want to find a differential equation for this motion. In an exam, folks, I'm absolutely confident this would be a show that question. So here is my situation. I have got my particle. The forces acting on it are as follows. So let's assume that it's to the right of the initial point of its displacement from some fixed point on the path. I've got a force of 7.5x driving it back towards that initial point. I've got a force of 6v, which opposes motion. So if v is to the right, it's negative. And then I've got a driving force of 12 sine t. So to write down a differential equation, we can use Newton's second law. If I resolve taking to the right as positive, the net effect of these forces is minus 7.5t minus 6v plus 12 sine t is equal to the mass, and we're told that the mass is 1.5 times the acceleration. Now that's turned into differential equation. We can replace v with dx by dt and a with d2x by dt squared, and this is going to give me minus 7.5x minus 6 dx by dt plus 12 sine t is equal to 1.5 times d2x by dt squared. Now to rewrite this in a form where we can solve it easily, I'm going to get all the terms on one side except keep the 12 sine t by itself, and that will give me 12 sine t is equal to 1.5 d2x by dt squared plus 6 dx by dt. plus 7.5x. And you can actually make the numbers slightly nicer by dividing throughout by 1.5. And I'm going to switch the two sides over as well, because that's our standard form. So the differential equation that this turns into is d2x by dt squared plus 4dx by dt plus 5x is equal to 8 sine t. That's the differential equation for part A. So that's just dividing through by 1.5 to simplify the coefficients and getting all the differential terms and the x terms on one side and switching them over. Okay, it then says solve the differential equation to find x in terms of t. Now, folks, I'm going to warn you here, this is a little bit full on, ladies and gentlemen, boys and girls. The first step for doing this is to find a complementary function. To do that, you write down the auxiliary equation, which is m squared plus 4m plus 5 is equal to 0. Solving that on your calculator, it turns out to have complex roots of the form m is minus 2 plus or minus I. So consequently, the complementary function, the f, is going to be x is e to the minus 2t brackets a cos t plus b sine t is the complementary function. However, in this case, because there is another function on the right-hand side, we need to find a particular integral. And the essential principle is you try something of the same form of the right-hand side. So my trial particular integral, because this is sine t, you have to try something which has got sine and cos term t in it. So I'm going to try x is p cos t plus q sine t. Now, the very, very, very observant of you might be a little bit concerned about doing that because there's a cos t and a sine t in the complementary function. But that's not a problem because it's multiplied by an exponential term. They're not separate terms in their own right. They are multiplied by exponentials. It's not going to cause a problem in this case, but we'll do another example in a second. I need to work out P and Q. To do that, differentiate twice and sub it into the differential equation to see what we get. So dx by dt is going to be P cos t differentiates to give minus P sine t plus Q cos t. If you differentiate again, d2x by dt squared is equal to minus P cos t minus Q sine t. Big deep breath. We can now sub that all into the differential equation and then compare coefficients to work out P and Q. So d2x by dt squared is minus P cos t minus Q sine t. Plus 4 dx by dt is going to be 4 times minus P sine t. Comes a minus. So minus 4P sine t plus 4Q cos t plus 5x is going to give me 5P cos t plus 5Q sine t, and that should be equal to 8 sine t. Now, when I compare coefficients, because there's no cos term on the right-hand side, the coefficients of cos t must turn out to give 0. So these are the cos t terms I'm underlining here. So if you compare coefficients of cos t, you will get minus p plus 4q plus 5p is equal to 0. That differential equation simplifies to give you, if you collect like terms, you get 4p plus 4q is equal to 0. Or if you like, you can divide by 4 to get p plus q is equal to 0. If you then look at the sine t terms, so the sine t terms are, we've got minus q sine t, minus 4p sine t, and 5q sine t. That must match up with the 8 sine t. So you will get minus q sine t minus 4p plus 5q is equal to 8. So what that's going to simplify to give is minus 4p plus 4q is equal to 8, or again, you can simplify to get minus p plus q is equal to 2. And that's an easy pair of differential equations to solve. You can, if you wish, do it on your calculator, or if you add them, the p's cancel, you'll get 2q is 2. So q is 1, and you'll get p is minus 1. But you can use your calculator if you want. So p is minus 1, and q is 1 is that. So what that means is that the particular integral, is minus cos t plus q sine t. So therefore, the general solution is going to be x is the complementary function, which is e to the minus 2t into a cos t plus b sine t, plus the particular integral, which is p, so that's minus 1 times cos t plus cos t plus q sine t, which is just sine t. Okay, to do with working out a and b, to do that, we can use the initial conditions which are given. So we know, first of all, when t is 0, x is 5. So if you substitute into this, t is 0, x is equal to 5, you'll get on the left, you just get 5. E to the minus 0 is just 1. A times cos of 0 is a. B times sine of 0 is just 0. And then take away cos of 0, which is 1, plus sine of 0 is 0. So that's going to give me a is equal to 6. To work out b, we're going to have to use the fact that the initial velocity is 2. So I need to get an expression for the velocity, which is dx by dt. So I'm going to differentiate my general solution. You can plug in a as 6 if you want. I'm just going to plug it in at a later stage. The first term will need the product rule, v du plus u dv. So that's going to give me minus 2 e to the minus 2t into a cos t plus b sine t plus u dv is going to give me e to the minus 2t into minus a sine t plus b cos t. You've also got to differentiate minus cos t, which will give me plus sine t, and sine t, which will give me just cos t. We know that when t is 0, v is equal to 2. So you're going to get on the left, 2 is. On the right, you are going to get minus 2 times 1 times a. So that's minus 2a. 1 times b, so plus b, plus 1. And if you rearrange that to get b, because we know that a is 6, that's going to be minus 12 plus b plus 1. That will give me that b is equal to 13. So consequently, the answer to part B is x is equal to e to the minus 2t brackets 6 cos t plus 13 sine t. Add the particular integral, which is minus cos t plus sine t, and we are done. That's the particular solution. Now, and that's as much work as you can possibly be asked to do, surely, for a question of this type. The last part says, describe the motion when t is large. And this is a slightly vague question, ladies and gentlemen, boys and girls. But let me give what I think is the fullest answer that I can do with this. So as t is large means t tends to infinity. Now, as t gets larger, this exponential decaying term, e to the minus 2t, will tend to 0. So the whole of the first term will approach 0. So you're going to get x is going to tend to minus cos t plus sine t. So that's an approximate expression for x for large values of t. I'm just going to rewrite this slightly. So this is the same as sine t minus cos t. That's what that gives you. And what that really means is that it will approximately exhibit simple harmonic motion. To work out the amplitude and the time period of that motion, that's a very vaguely worded question. I think it would be enough to say x oscillates or x has simple harmonic motion approximately. To work out the amplitude and the time period, I'm going to rewrite that in the form r sine x plus alpha or r sine x minus alpha. So by standard A-level maths methods, this can be rewritten as root 2 sine of t minus pi over 4. So what that means is that x will oscillate or have simple harmonic motion. With simple harmonic motion, the amplitude is equal to root 2, and the time period is just, well, this is just a sine function that's been translated in the x direction and stretched in the y direction. The time period is 2 pi. And we are done. Right, folks, one more of these to do, and then we are done with this topic. I do appreciate the questions that arise in this topic can be very full on and time consuming. So this question, we are given that the vertical displacement of part of a bridge from its equilibrium position, y meters at time t seconds, is modeled by this differential equation here. Let's just use my highlighter pen. Let's go with it. So d2y by dt squared plus 4y is 0.04 sine 2t. Initially, which means when t is 0, y is 0, and dy by dt is 0.03, we were asked to first of all solve the differential equation to find y in terms of t. Now, can I first of all say that this is perhaps typical of a real exam question in that we don't need to derive this differential equation. It's purely been given for us. But can I warn you, this one gets quite time consuming. So that's why I'm talk through very carefully my model solutions for this. So in order to solve the differential equation of this type, you need to first of all write down your auxiliary equation. So the auxiliary equation corresponding to this differential equation is m squared plus 4 is 0. You solve that on your calculator or by just making m squared the subject, it's minus 4 and square rooting, and you get m is plus or minus 2i. So consequently, the complementary function is, well, there would be an e to the power of 0t in front, but 0t is 0. Therefore, e to the power of 0t is just 1. So the complementary function is just a sine 2t plus b cos t. Then you write down a particular integral. Now, looking at the right-hand side, 0.04 sine 2t, usually you would try an expression of the form p cos 2t plus q sine 2t. However, those are the terms in the complementary function. If you do that, differentiate it twice and sub in, it will all give you 0. So consequently, you have to put an extra factor of t in front. So the trial particular integral we use is not y is p sine 2t plus q cos 2t, as they're terms of the complementary function. It's y is pt sine 2t plus qt cos 2t. And I'm going to need to differentiate that twice and then sub it into the differential equation and compare coefficients to find p and q. So guys, choice. What I've done is I've factored out t. I'm going to need to use the product rule to do this. If you factor out t, it means you can get away with just using the product rule once. If you don't factor out the t, you have to use the product rule twice. So y is t brackets p sine 2t plus q cos 2t. By the product rule, dy by dt is u times dv is t brackets 2p cos 2t minus qt sine 2t plus v times du, well du is just 1, just gives me p sine 2t plus q cos 2t. So you don't have to take t out as a factor, but if you don't, you end up having to use the product rule about 6 times in this question. We need d2y by dt squared, so we've got to do that again. So d2y by dt squared is, by the product rule, u times dv is t into minus 4p sine 2t minus 8q cos 2t, plus v times du is 2p cos 2t minus 2q cos 2t. That's because if you differentiate t, you get 1. And then if you differentiate the extra term at the end, differentiate that bit, there you get 2p cos 2t minus 2q cos minus 2q. There's a mistake there, folks. Let me just change that slightly. Dun, 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 dun. So 2t that minus 2q, that should be a sine 2t there. Dun, 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 dun. Okay, it's a slight mistake there. If you simplify this, you can collect together terms in the last bits, folks. So you get t into minus 4p sine 2t minus 4q cos 2t plus collecting 2p cos 2t plus another 2p cos 2t is 4p cos 2t minus 4q sine 2t. If you now sub that back into the entire differential equation, this is what you will get. You will get d2y by dt squared is all of that stuff. T into minus 4p sine 2t minus 4q cos 2t plus 4p cos 2t minus 4q sine 2t, and then plus 4y is plus 4t sine 2t plus q cos 2t. And the good news is, if you look carefully, that bit there and that bit there just completely cancel out. So all we're left with is 4p cos qt minus 4q sine 2t is 0.04 sine 2t. If you now compare coefficients, there are no cos t terms on by the other side. So 4p must be 0, so therefore p must be 0. If you compare coefficients of the sine t terms, on the left you get minus 4q is 0.04, so therefore dividing through by minus 4, q is 0.01, minus 0.01. So here is my general solution. Y is the complementary function, a sine 2t plus b cos 2t, plus the particular integral, so the cos 2 was equal to minus 0.1 t times cos qt. That's what we're going to get for that, because the sine 2t term is 0. To now work out a and b, we are told initially, which means when t is 0, y is 0. So therefore, on the left-hand side, you get 0. If t is 0, sine of 0 is 0, so the a term becomes 0. Cos of 0 is 1, so you get b. And then the last term is 0 because of this factor of t in it. So that means that b is equal to 0. Then, to work out a, we've got to use the fact that we know what initially dy by dt is. So if you differentiate this, you're going to get 2a cos 2t minus 2b. Oh, so that term is just 0 already, so we don't have to worry about that term because b is 0. If you use the product rule to differentiate minus 0.01 t cos 2t, u times dv is minus 0.01 t times minus 2 sine 2t, so that gives you 0.02 t sine 2t. And then u times dv is minus 0.01 cos 2t. If you sub into that, when t is 0, dy by dt is 0.03, you will get on the left 0.03, on the right 2a, the 0.02t sine 2t term is 0 minus 0.01 because cos of 0 is 0. And if you rearrange that, a turns out to be 0.02. So consequently, here is my formula for the displacement y against t. Y is 0.02t minus 0.01t cos 2t. And we have done that. Now, in this case, there's an extra bit which says explain why this model cannot hold in the long term. So this indicates that something must go wrong when t gets large. Now, the first term is just a trig function, a multiple of sine 2t. That's just going to oscillate between a minimum and maximum values of 0.02. But there is a bit of an issue with the second term. The second term has got a factor of 0.02t in front of it. So it's a cos function, but it's multiplied by 0.01t. And as t gets larger, the amplitude corresponding to that bit is going to get larger and larger and larger. So this is the reason why it will fail. As t tends to infinity, 0.01t is also going to tend to infinity. So consequently, minus 0.01t times cos 2t will oscillate between increasingly large positive and negative values. So consequently, the whole function is going to oscillate between increasingly large positive and negative values with no limit. And that's not possible. The displacements of the bridge cannot get as large as you want. The bridge will collapse. Okay, folks. Now, the stuff on the bottom of the page isn't really on the syllabus, but this previous example here is illustrative of a situation that does sometimes happen in nature. There are famous examples of this happening. It's because the system's natural frequency is the same as the driving force's natural frequency, and this can lead to oscillations with an increasing amplitude, as shown by this graph. And there are famous examples of this happening in nature. There's a famous thing called the Tacoma Bridge disaster, where a bridge was designed, the wind started blowing it, and the amplitude of the oscillations got larger and larger and larger, and the bridge collapsed. Engineers need to take this into account when they are designing structures, and engineers will try to make sure that the natural frequency of any structure they build is so high that any forced frequencies are bound to be lower than it. Okay, folks. Oh, you can now do the exercise on the next page. There you can have a go at that, folks. Okay.